There's a signal sitting in an archive at the Space Telescope Science Institute right now, a faint glow in mid-infrared light captured by the James Webb Space Telescope that scientists spent years trying to prove was even real. No telescope before Webb had ever separated this glow from its neighbor. No model of a small, sunlight-starved world was ever supposed to behave quite like this. No prediction this specific has ever been confirmed this precisely, this far from the world that made it. It is not a snapshot. It is a heartbeat, recorded for the first time. Stay with me, because what Webb found doesn't just describe Pluto, it rewrites what an atmosphere is allowed to do this far from the sun. If you're new here, this channel breaks down real space discoveries with zero filler, so if that's your thing, subscribe now. It's free. Let us go back to the beginning. On July 14, 2015, NASA's New Horizons spacecraft skimmed just 7,800 miles above Pluto's surface, the closest any human-made object has ever come to the dwarf planet, and in a matter of hours it rewrote 3 decades of assumptions. Before that flyby, Pluto was widely treated as a frozen, geologically dead relic, a reasonable assumption given its distance and its tiny size. What New Horizons found instead was a world with mountains of water ice, a heart-shaped basin of nitrogen glaciers called Sputnik Planitia, and, almost as an afterthought in the excitement, a thin blue haze ringing its horizon, backlit by the sun. That haze was strange, but nobody had the tools to say exactly why yet. It was visible only because New Horizons caught the sunlight scattering through it at a steep, backlit angle as the spacecraft looked back over its shoulder after closest approach. The same geometry that would later make it famous in one of the mission's most reproduced images. Pluto's atmosphere, made mostly of nitrogen with traces of methane and carbon monoxide, was measured at a surface pressure of about 10 microbars. Translate that. Earth's atmosphere presses down on you with roughly 1,000,000 times more force than that. Pluto doesn't really have air. It has a rumor of air, clinging to a world sitting, on average, 39 times farther from the sun than Earth is. Before New Horizons, most of what astronomers knew about Pluto came from blurry pixels and indirect measurements. A world discovered in 1930 by Clyde Tombaugh, studied for 85 years almost entirely as a point of light, its surface features essentially guessed at through decades of ground-based observation and a handful of grainy Hubble images. That 2015 flyby changed everything in a single pass, because a spacecraft only gets one shot at a target moving this fast, this far from home. There is no orbit insertion at Pluto, no second attempt, just a narrow window of a few hours to gather everything humanity would know about this world firsthand for the foreseeable future. What New Horizons returned in that window justified every year of the 9-year journey it took to get there. Nitrogen ice plains stretching across Sputnik Planitia, water ice mountains rising several kilometers into a nearly non-existent sky, evidence of ongoing geological activity on a world many scientists had assumed was long dead. Here's where the old, entirely reasonable model comes in. For decades, scientists assumed thin atmospheres like Pluto's behaved the way most planetary atmospheres do, warmed by sunlight, cooled by the slow radiation of gas molecules themselves, following the same basic energy rules that describe Earth's or Mars's air. It was a sound assumption, built on the physics that had worked everywhere else. But in 2017, a planetary scientist named Xi Zhang at UC Santa Cruz published something that struck many of his peers as a crazy idea, in his own later words, and that Pluto's haze, not its gas, was actually running the show, absorbing sunlight during the day and releasing it back into space as infrared heat at night, cooling the atmosphere far more efficiently than gas alone ever could. If Zhang was right, that haze should be glowing faintly in a specific band of mid-infrared light. There was just one problem. No instrument in existence had the sensitivity to detect it. And even if one did, there was a second problem baked into the geometry of the Pluto system itself, one that would take another 5 years and a brand new space telescope to solve. Set that aside for a moment. It matters more than it sounds like it does. Webb launched on Christmas Day 2021, and by October 2022 it was finally pointed at Pluto, using an instrument called MIRI, the mid-infrared instrument, tuned to wavelengths between roughly 5 and 28 microns, a range no prior telescope had ever explored at Pluto with any real precision. This is not a small technical footnote. Every previous generation of infrared observatory capable of studying the outer solar system simply lacked the sensitivity to pick out a signal this faint, this far away, buried in wavelengths that Earth's own atmosphere blocks almost entirely, which is precisely why an instrument had to be lofted 1,000,000 miles from Earth, past the Moon, to a gravitationally stable point called L2, just to have a chance at catching it. And what it found, once scientists finally finished untangling the data, was exactly the signature Zhang had predicted 5 years earlier. Pluto's upper atmosphere sits at approximately minus 333 degrees Fahrenheit, minus 203 Celsius. Read that again, because the number itself isn't the discovery. The discovery is what that number is not. Based on gas physics alone, models expected Pluto's upper atmosphere to be roughly 30 degrees Fahrenheit, warmer than what Webb actually measured. 30 degrees may not sound dramatic until you remember the scale we're working at. This is a world already so cold that nitrogen freezes solid on its surface, and Webb still found it running significantly colder than the numbers said it should be. Here's the delayed reveal. This is not a planet cooled by starlight. This is a planet cooled by the fog floating inside its own sky. The mechanism, once confirmed, was almost elegant in its cruelty. Pluto's haze particles, complex organic molecules born when sunlight breaks apart methane and nitrogen high in the atmosphere, behave like millions of microscopic radiators. During Pluto's brief day, they soak up what little solar energy reaches this far out. At night, they release that energy back into space as infrared light, far more efficiently than a thin cloud of plain nitrogen and methane gas ever could on its own. Tanguy Bertrand, an astronomer at the Paris Observatory who led one of the analyses, called it a new kind of climate. Not a copy of Earth's, not quite a copy of Titan's either, despite some surface similarities, but its own distinct system, one that had never been directly observed anywhere else in the solar system before Webb pointed its mirror at this particular dim, distant world. Here is where this stops being abstract. Jung and his colleagues weren't just chasing a curiosity about a dwarf planet on the edge of the solar system's map. They were chasing a proxy for something much closer to home. Billions of years ago, before oxygen existed in Earth's atmosphere, our own planet was wrapped in a nitrogen and hydrocarbon haze not entirely unlike what Webb just confirmed on Pluto, a chemically primitive atmosphere, driven by many of the same photochemical reactions, existing in the window of time before life had reshaped the air we now breathe. Bertrand has said as much directly. By studying how Pluto's haze governs its climate today, scientists gain a working laboratory for the kind of atmosphere early Earth may have had. The raw chemical starting conditions that eventually somehow became habitable. A hazy sky 10 billion kilometers away, or maybe quietly holding a piece of the answer to how our own world became the one place we know of where any of this mattered. Think about what that means practically. We cannot travel backward in time to sample Earth's own primordial atmosphere directly. That chemistry vanished billions of years ago, overwritten first by early microbial life and then by the oxygen revolution that made animal life possible at all. What we can do is travel, in effect, sideways. Find another world running a broadly similar chemical experiment today, still frozen at an earlier chapter of the process, and read its atmosphere like a preserved page from a book Earth itself burned long ago. Pluto, against every expectation anyone ever had for a small, frigid world at the edge of the solar system, turns out to be exactly that kind of page. But confirming any of it very nearly didn't happen, not because the physics was wrong, but because of simple geometry. Pluto and Charon, its enormous moon, are locked in a tight mutual orbit just under 19,600 kilometers apart, tidally bound, so that each always shows the same face to the other, circling one another every 6.4 days. From Earth, and even from Webb's vantage point roughly 3.5 billion miles away, that separation translates into an angular distance of only about 0.68 to 0.78 arc seconds, an almost unimaginably small sliver of sky. And here's the problem nobody could design around. The blur inherent in Webb's own MIRI instrument, the unavoidable smearing of light called its point spread function, measures roughly 0.49 to 0.80 arc seconds at these wavelengths. Sit with that for a second. The gap between two entire worlds and the built-in fuzziness of the most powerful infrared eye humanity has ever put in space were almost exactly the same size. At these specific wavelengths, Pluto and Charon threatened to blur into a single indistinguishable smudge of heat, which meant every earlier mid-infrared attempt at this system, going back to a European infrared observatory in 1997, NASA's Spitzer Space Telescope in 2004, and Europe's Herschel Space Observatory in 2012, had returned only a jumbled combined signal that could never be confidently split apart. Think about what that actually meant for the team proposing this observation. They were asking one of the most oversubscribed scientific instruments ever built to attempt something at the absolute edge of what its optics were physically capable of resolving. Not a comfortable margin, not a wide buffer, but a target sitting almost exactly on top of the telescope's own blur limit. Every other object Webb has famously imaged, from distant galaxies to nearby exoplanet systems, benefits from angular separations far more forgiving than this one. Pluto and Charon offered no such comfort. If that problem went unsolved with Webb 2, the entire 5-year chase to confirm Jung's haze hypothesis would have hit a wall it might not clear again for a decade. Webb's observing time is fiercely oversubscribed, competed for by thousands of scientists across every field of astronomy, and a failed attempt doesn't simply get quietly rescheduled next month. So the team, led by Emmanuel Lelouch at the Paris Observatory, built their observing plan around the one variable they could control: timing. They scheduled 6 separate visits to the Pluto-Charon system across a single 6.4-day mutual orbit, spaced 60 degrees apart in orbital longitude, deliberately catching the pair from multiple angles as they wheeled around their shared center of mass. Then came the harder part, not collecting the light, but untangling it. Scientists applied a technique called point spread function fitting, essentially building a precise mathematical model of exactly how Webb's own blur behaves, and using it to statistically pull apart which fraction of the smeared light belonged to Pluto and which belonged to Charon. It was painstaking, uncertain work, run against a target so close to the telescope's own resolving limit that success was never guaranteed until the numbers actually converged. And in October 2022, followed by a deeper spectroscopic look in May 2023, they converged. For the first time in the history of astronomy, scientists had 2 separate confirmed thermal light curves, one for Pluto, one for Charon, pulled cleanly out of a blur that had defeated every telescope before Webb. It was, in the words of researchers involved, the first detection of Charon's own thermal light curve ever recorded, not a byproduct, not an approximation, but a clean, standalone measurement of a body that had spent nearly 3 decades hiding inside its larger companion's glow. And once Pluto's own signal stood fully alone, stripped of any contamination from Charon, the deeper spectroscopic follow, up in May 2023, could finally do what Zhang's 2017 paper had only theorized about. Read the full mid-infrared fingerprint of Pluto's atmosphere, isolated, unambiguous, and ready to be checked line by line against a 9-year-old prediction. Here is what is happening right now in 2026. Stellar occultations are not glamorous events. No dramatic imagery, no close-up photographs, just a distant star's light flickering and dimming for a matter of seconds as Pluto's paper-thin atmosphere passes in front of it, observed from precisely positioned telescopes scattered across whatever narrow strip of Earth happens to fall inside the shadow's path that night. It is slow, patient, unglamorous science, repeated year after year, decade after decade, by researchers chasing shadows across oceans and uninhabited land just to catch a few extra seconds of data. Just days ago, a team led by Amanda Sikafous at the Planetary Science Institute published a new study built on 10 separate stellar occultation events, moments when Pluto passes directly in front of a distant background star, briefly dimming its light in a way that reveals the thickness of the atmosphere it passes through, spanning the years 2017 through 2023. The results were unambiguous in a way earlier smaller studies hadn't been. Pluto's atmospheric pressure held essentially steady from the 2015 New Horizons flyby through mid-2021. Then, between mid-2021 and July 2023, that pressure dropped by 16%, not a rounding error, not noise in the data, a real measurable decline consistent across 10 independent observations using one unified method, the strongest evidence yet that Pluto's atmosphere has begun doing exactly what physics always said it eventually would, freezing back onto the surface as the planet's long, cold retreat from the sun continues. Earlier, smaller studies had disagreed sharply. One team reported freezing as early as a 2018 event. Another found no drop at all by 2020 and described the atmosphere as sitting in a stable plateau. Sikafous' 10-event dataset is the first to cut cleanly through that disagreement using consistent methodology across 6 years. The haze that Webb confirmed is cooling the same atmosphere, quietly, wavelength by wavelength, while ground-based telescopes now confirm that atmosphere is measurably beginning to disappear. And there is an exact date attached to where this is all heading. Not an estimate, not a rough projection, but a number locked in by orbital mechanics as precisely as any calendar event humanity has ever calculated. Pluto reached its closest approach to the Sun in 1989, and it has been retreating on its 248-year orbit ever since. A retreat the small world has not made even once since its discovery in 1930, because no human alive at the time of that discovery has lived long enough to see Pluto complete even half a lap around the Sun. That outward drift continues and continues and continues until it reaches its exact turning point. Aphelion, the single farthest moment in Pluto's entire orbit, arriving in February of 2114. A date fixed by gravity and geometry, not opinion, roughly 49 astronomical units from the Sun at its most distant. Between now and then, sunlight reaching Pluto keeps thinning, temperatures keep falling, and by every serious model currently in circulation, the atmospheric decline Sikafous' team just confirmed keeps accelerating for decades to come, before Pluto finally, slowly, begins its multi-century turn back toward the light. Nobody watching this video will be alive to see that turnaround happen. Nobody currently working at the Planetary Science Institute, nobody at the Paris Observatory, nobody at JPL will be either. February 2114 is not a projection anyone is hedging on. It is a fixed point on an orbital clock that started ticking long before Pluto was even discovered, indifferent to whichever models about its atmosphere ultimately turn out to be right. Now, the part that doesn't resolve cleanly, because science doesn't owe anyone a tidy ending here. Exactly how far this collapse will go is a genuinely open argument among the scientists studying it. One line of thinking, grounded in the newest volatile transport models, suggests the atmosphere will decline sharply but not vanish completely. Buffered by the sheer volume of nitrogen ice sitting in Sputnik Planitia, that heart-shaped basin New Horizons photographed in 2015, acting like a vast reservoir slowly releasing gas even as pressure falls elsewhere. A second line of thinking, rooted in older 2019 modeling, projected something closer to a full collapse. By around 2030, the atmosphere frosting out almost entirely across the whole planet. Bright new frost, reflecting sunlight and possibly making Pluto noticeably brighter in the sky as a direct result. Both camps are working from real data, real physics, and real disagreement about how much buffering capacity that nitrogen reservoir actually provides once temperatures drop far enough. Earlier occultation studies only deepened the confusion rather than resolving it. One team studying a 2018 event reported clear evidence of freezing already underway, while a separate French-led team observing a 2020 event found no drop in pressure at all and described the atmosphere as sitting in a stable plateau, not a decline. Two respected research groups, two contradictory readings of the same slow-moving planetary event, separated by only 2 years of observation time. What most people are not seeing in the headlines is that these two pictures haven't been fully reconciled. Sisyphus' own team is careful to say the decline has clearly begun, that much is now settled, but whether it ends in a stubborn partial equilibrium or something closer to total freeze-out is still an active, unresolved modeling question, one that will likely take another decade of occultation data to settle either way. Zoom out from Pluto for a moment, because there's a pattern here worth naming. Webb was built, funded, and launched primarily to look outward, toward the earliest galaxies, toward light that had been traveling since almost the beginning of the universe itself. Nobody designed its flagship mission around, a dwarf planet 3.5 billion miles from home. And yet, some of its most quietly significant science has turned out to be exactly that, confirming a 9-year-old hypothesis about a hazy little world most people had stopped thinking about the moment New Horizons flew past it. This is what real scientific progress actually looks like, far more often than the highlight reels. Suggest not a single instrument built for one triumphant answer, but a general-purpose tool aimed at everything, occasionally solving a problem nobody built it specifically to solve. The technical achievement matters just as much as the discovery itself. A telescope engineered to resolve galaxies at the edge of observable. Time had to be pushed to the very edge of its own optical resolution just to tell two nearby worlds apart. And it did, through nothing more exotic than careful scheduling and patient mathematics. Power, in this story, was never really about brute strength. It was about precision applied at exactly the moment precision was needed most. There's a second, quieter lesson buried in the 7 years, between Zhang's 2017 paper and Webb's 2022 confirmation. Good science is often just a correct idea, published years before anyone has the tools to prove it, sitting patiently in the literature while engineers somewhere else finish building the instrument that will eventually catch up to it. Zhang described his own hypothesis as a crazy idea that drew real skepticism from colleagues at the time, and he was right anyway, years before he had any way to demonstrate it. The gap between a correct prediction and its confirmation is not a flaw in how science works. It is the entire mechanism. Ideas outrun instruments constantly. Then, occasionally, the instruments catch up, and something that sounded speculative becomes a settled measurement, footnoted in every future study of this small, cold world. There's a photograph from that 2015 flyby that keeps surfacing in every retelling of Pluto's story, and it earns the repetition. New Horizons, looking backward after its closest approach, catching sunlight scattered through Pluto's thin atmosphere from behind, turning the whole rim of the planet into a soft, glowing blue ring against total darkness. That blue is the haze. The very haze Webb would spend the next 7 years proving actually runs Pluto's climate, cooling a world already colder than almost anywhere else humans have ever measured anything. It is strange to think of something that thin, that faint, as powerful enough to reshape an entire planet's temperature. But it is. And it is stranger still to think that this same haze is now measurably thinning, retreating, freezing itself back onto Pluto's surface a little more each year. A slow exhale from a world settling into a winter that will not end within any human lifetime. Not this generation's, not several generations. From now. Somewhere in that heart-shaped glacier of nitrogen ice, frozen air is quietly returning home. There is no camera running out there right now to record it happening. New Horizons is long gone, decades into its own onward journey through the Kuiper Belt, and no other spacecraft has ever been sent back. Everything we know about this slow winter is being pieced together secondhand. A telescope 1 million miles from Earth reading Pluto's borrowed heat, and a handful of researchers on the ground, timing the flicker of starlight as it passes through an atmosphere that is, patiently, molecule by molecule, choosing to stop being an atmosphere at all. Nobody will be there to watch the last of it settle onto the ice. We will only ever have the shadow it left behind, and the models built to read that shadow correctly. So here's everything in order. New Horizons revealed Pluto's hazy active atmosphere in 2015, and in 2017, Xizhang predicted that haze alone was cooling the planet more efficiently than gas ever could. A hypothesis no instrument could test until Webb launched in 2021. In 2022 and 2023, Webb's MIRI instrument finally separated Pluto's heat signature from Charon's, despite the two worlds sitting almost exactly at the telescope's own resolving limit, confirming Pluto's atmosphere runs roughly 30 degrees Fahrenheit colder than gas-only models predicted. That haze may even mirror the atmosphere of early Earth, before oxygen, before life. Meanwhile, new 2026 ground-based data confirms Pluto's atmospheric pressure has already dropped 16% since 2021, the first solid evidence of a freeze-out that will continue accelerating until Pluto reaches the farthest point in its 248-year orbit in February of 2114. And whether that freeze-out ends in partial balance or near total collapse is still genuinely unresolved, with competing occultation studies from 2018 and 2020 having already reached opposite conclusions once before. If this kind of deep, sourced dive into what our solar system is actually doing right now is your thing, subscribe and turn on notifications. I'll be covering the next occultation results the moment they're published. Here's my question for you. If you could send one more spacecraft anywhere in the solar system right now, would you send it back to Pluto for a second look, or somewhere humans have never been at all? Tell me in the comments. I read every single one,